Hello, everyone. My name is Fabian. I'm supervised by Associate Professor Ed Cripps, Professor Mark Jessel, and Dr. Mark Lindsay. I'm going to talk to you about my work on deep learning and Bayesian methods for mineral resource estimation. So the outline, very short on time, so we'll do a quick introduction with some context and motivation for this work. And then I'll talk to you about independent part of my work. So in this work, we're trying to introduce modern techniques from the statistical and the deep learning literature into mineral resource estimation, which is currently uses very traditional methods. And for some context, mineral resource estimation is a part of the mining value chain where after exploration, we want to make sure that the material we're interested in is actually economically viable to extract. So after exploration, we zoom into a zone and make sure that we can actually construct a mine in this area. Well, resource estimation has many steps, and we're just focusing on the spatial interpolation parts of it. This is representation of what the problem usually looks like spatially. We have a lot of drill holes with data, and we want to know what's in the middle. So I'll jump into after the motivation. Resource estimation uses outdated methods for a good reason, and it's because it's such a crucial part of the mining value chain that they really have to be sure that the models work. Because as people have mentioned before, irreversible decisions are going to be made, and you need to have confidence in the model. So first, I'm going to talk to you about our work on interpreting deep kriging for spatial interpolation. So what is this? We take the properties of a rock, including its spatial location. We do a transformation on the XYZ coordinates, input this into a deep neural net, make some predictions, and then try to attempt to interpret the predictions that were made. So, well, the motivation, as we said, in this day and era, we have more data available with the drill holes, and there are powerful alternatives to the current methods that are being used in this, namely kriging and inverse distance weighing. But these more powerful methods are less interpretable. Some of them are not apt for spatial interpolation and are also not very proficient at generating uncertainty estimates. We're only going to attack the first two in this work. We're not going to focus on the uncertainty quantification, which is a big topic in itself. So the aim is to investigate whether we can use a modern method in this discipline, and if we can extract some value from it, acknowledging that it is very challenging given the problems that I've outlined. So we want to attack the spatial interpolation capabilities of deep learning first, because they're not very good at it in the base form. And for that part, Chen in 2020 made a big contribution, which helps a lot because, well, he's proven that if you expand the feature space using the Cahoon and Leal theorem, you can help the neural net learn the spatial correlations without any additional information. So you just have the XYZ coordinates and you do a basis function representation of that and input that into the network, and it'll produce better results doing spatial interpolation. So we use that model. First, we make sure that it actually performs well in this context. And then we move on to the interpretability part, which is the big contribution of this work. So we use a number of covariates that come from the drill hole, and the rock density is the target variable in this case. We do some comparisons to kriging and a vanilla deep neural net, These are just visual comparisons to make sure that everything was in order. And we also do numeric comparisons using some accuracy metrics. And deep kriging does in fact perform much better than an equivalent deep neural net with everything equal but the feature expansion. And it also performs mostly better than kriging, except for one metric in the case with additional variables. So after we've proven this, we move into interpretability part. And to illustrate what we're trying to do here, I'll first talk about a very simple case where, let's say, density can be represented just by the depth of the area we're looking at. In this case, a linear regression would suffice, and we would know exactly how density depends on depth. But in the real world, there are more challenging, more complex relationships actually going on. And this is actually also simplified, just a little bit more realistic. And in this case, you can still represent the relationship between density and depth. You need more parameters, but it is still possible. But when you move on to 4, 5, 6 variables, you require a more advanced approach. So that's what we do here. We use Shapley values, which to explain what they are, we first talk about loco, which is a very straightforward method of just fitting an estimator and then fitting the estimator, the same estimator, but without one of the variables, and measuring the difference between the predictions those two make in order to measure the impact that feature we removed had on the predictions. This doesn't work in the case of more complex relationships like the one we just showed, because there are feature interactions. So Shapley values approaches this by calculating this local, but for every single subset of features from the feature space. So you take the power set of the feature space and then calculate this for all of them. And then using some combinatorics, you take the average of all those subsets. And after summing all that, you get the Shapley value for the feature you're investigating. So just to give some intuition into how to understand what Shapley values are actually doing, I like to illustrate it with an example of a team of specialists working on a research project, and the target variable being the research outcome. So let's think of a team with hydrologists, data scientists, statisticians, environmental engineers. And let's think the data scientist wants to join one of those two teams. And let's think of in what team would the data scientists be more valuable, given the people that are already in the team, right? In order to answer this question, we need to take two things into account. So how much new information does the data scientist add to the team? So how much new expertise does he add? And how much synergy does the data scientist have with the other members of the team? I don't want to give an answer to that question because it could offend sensibilities, but you can draw your own conclusions from where they would be more useful. And well, in our study, the problem is with the deep kriging feature expansion we did. We have too many features. So the combinatorial problem I just showed before is intractable, and it's not even close. So we did a simple but clever solution to this, which was what we call batch Shapley. We adapted the algorithm. So we're not evaluating features anymore. We're now evaluating groups of features. And we grouped all the basis functions together because we can simply do that because they do not have an individual meaning. And when you group them together, they do. Okay, I'll wrap it up. Thanks. That was a lot more, but I went too slow. Thanks.